Good morning, everybody. So let us start our lecture today, and today is October 26, 2021. So, okay. First of all, let us open our syllabus. Okay, so this is the syllabus. I uploaded a newer version of the syllabus. It is not new for the syllabus. There is nothing changed in the syllabus. Just I changed the schedule. Okay, so don't be misled that I'm updating or changing the syllabus. Just updated the schedule. So schedule was tentative from the very beginning. Okay, so according to our schedule, so your test will be this week, right? So next lecture, the 28 October 28, your test 2. So test 2, I'm making it like MCQ type. There will be about 50 MCQ type questions, and all from the slides, almost all from the slides, chapter 5 to chapter 9. So 5 is linked list, as you know that we skipped linked list from our test 1. So this linked list, stack, kiwi, and recursion. Okay, so in the test, we will cover only linked list, stack, kiwi, and recursion. So almost all of the questions you will see from content, from the content tab, then go to this module, and then download the modules. And as we are discussing for this module, linked list, stack. For instance, if you go linked list, you see that the chapter there is PowerPoint slide. Okay, so linked list, I already downloaded this for linked list, stack, and kiwi. For instance, let me go there quickly. Okay, so linked list, this is the slide we covered in our lecture, right? So please make sure that you read thoroughly the slides. Okay, this is linked list, and the next one is stack. Okay, stack. So in the test there will be no program programming code, but there will be some, maybe there will be some programs or instructions or pseudocode given, and you may be asked to find the actual code. Or if there is some codes, then you may be asked to correct the code if there is a mistake. Okay, so mainly go through the slides. Okay, I will go through the slides. Then more, all questions are from the slides. Okay, and then recursion, right? And then recursion. So all questions from the slides, but if you have, you need to study ahead. If you do not study, then the test time you will not have enough time to study and understand this from the slides and then to answer those questions. Okay, you have to study ahead of time. Okay, so this is the main announcement in this for this course. So I sent out this announcement this morning. Okay, so the regular time is actually an hour, so I extended it. I extended for 15 minutes more. Okay, and if you are entitled for an extended time, then please let me know. Send me an email. then your extended time will be 60 minutes. Okay, that's 60 minutes of original time. So I gave 15 minutes to everybody. So as we said that we will cover from chapter 5 to 9, linked list, stack, QE, and recursion. Does anyone has any question about the test? Okay, so if you are, okay, I'm sorry. This is the section 3. Oh, there is a mistake. I'm fixing it. Okay. There is a mistake. So your test time will be 11. So it will be 10 from 10:45. I'm sorry. 10:45 a.m. until our classes end at 12:15. So 12:30 p.m. Okay. Regular. Okay, so okay, so actually the 24 hours for the section 2 for online section, completely online section, asynchronous online section. But both sections have different questions. Okay. Okay. Does anyone has any question? Remember that your test will be during your regular class time. Okay. Okay.
Sounds good.
Okay. So now let us see our schedule. So we are discussing binary search tree, right? We are discussing trees. So in last lecture we started binary search tree, BST. So then BST actually has many implication and application and use. So later you will see that there are many other types of trees like APL trees, red blood trees. Those are based on binary search tree. So since this week we have a test, so I think I'll complete BST today. So let's see our it's not QE. Okay, so in our last lecture we are discussing binary search tree. This is our tree, this is our slides. Okay. So tree, we know that binary, there may have different kind of trees. For instance, this one is a regular tree. Okay, so in binary search tree, for each node, there can have maximum 2 children. It can have no child. For instance, K, L, and M. These nodes do not have any child. And for E, there are 2 children, and H has 1 child. D has 2 children. A has 3 children. C has 3 children and a grandchild. Okay. and A is like B has one child but two grandchildren. Okay, it can be have any format, but in a BST, in a binary search tree, there are some special characteristics of binary search tree. For instance, each child may have maximum two children. Okay, either one children or one child or two children or no child. Okay, that is one criteria. And another criteria is that is the left child always minor or lower than the root or parent. Root. We don't say parent actually, root. Okay, and the right child is always greater than the root. So here let us see whether this represent a BST or not. So 31 is our root. So 16 is less than root, so it will be on left side. Okay. Then 24 is greater than 16, so it will be greater than it will be right side of 24. Now let us compare 24 with the root. So it is 24 is less than the root is 31. So here 24 is on the left side of 31. You see that this is the left, this entire thing, this entire part is the left. This entire part is the left subtree, and this part is the right subtree. Okay, then 29 is greater than 24, it is on right side, greater than 16 on the right side, but it is less than 31, so in the left side of 31. Okay, and 19, so 19 is less than 24, so left side of 24, but it is greater than 16, so right side of 16. Okay, so 7 is less than 16, so in the left side of 16. Now if another node comes in with data value, for instance 12, so the where that should go? Can anyone please tell me? If we have another data value node, another node that has value 12, that where that 12, that node will go?
Go on the right side underneath 7.
Yes, that will go to the right side of 7, right? So 12 will be here. Okay. Now if it comes up another value with 10, then where that should go?
Would that go on the left side underneath 12?
Yes. 10 is here. Okay. So in this way, a binary search tree, so is binary search tree BST grows. Okay. Now it may happen for some rare cases, for some exceptional cases, that by this binary tree, for instance, this is growing pretty smoothly. For instance, here the height will be log with base 2 and pretty log base 2 and n is the number of number of elements. So, but in some cases, for instance, if the data value appears in this way, 7, then 10, then 12, then 16, then 19, then 24, 29, 31, 45. If our data values come this way, then the BST will grow like this, 7, and then 10 on the right side, greater than 7, and then 12, the right side will go the right side of 10, and then 16 will go right side of 12, and then 19 will go right side. Similarly, 24 will go right side, and similarly 29 will go right side, and then similarly 31 right side, and 45 will go right side. So this tree, you see that this is growing linearly. So in order to do a search operation, for instance, here we need to do big O of n. So this is like a linked list, right? It looks like a linked list. So in that case, this BST is BST, but it is not efficient. So in order to resolve these kind of issues, okay, to ensure that the binary search tree would be self-balancing, then there are different other kinds of binary search tree that are called AVL trees that got red black trees. So those are not in the scope of this course. Whenever you take your algorithm analysis or advanced data structure course, then you will know this. Okay, but whatever you just got an idea that the BST sometimes can grow linearly for some exceptional or cases. Okay. So, and how do we implement a linked list for a BST? We can implement a BST like a linked with a linked list. Okay, linked list implementation, it can have linked list implementation easily. So linked list implementation, for linked list implementation, each node will have 2 pointers, 2 links. We know that in a linked list, each node has 2 pointers, one for data, another for link, right? Data and 2 parts, one link and then data. So, but here the link, there will be 2 links, and then one also data for the data, and the 2 nodes, one for right, another for left, right and left, right and left. For all the way end, the right and left will be null value. So here in picture, so that they put cross to indicate null, to denote null. So we discussed this and we gave some homework for this one, traversal. Okay, now let us go through this binary search tree. Okay, we discussed this in our last lecture. Okay. So we said that on the right side is not a binary search tree. What is the reason that the right side? The right side is not a BST. For which node? The right side, this is not a BST. What is the node for which this is not a BST? Do you understand my questions? So which node is responsible for not to be a BST? For this tree, which node is not responsible? Which tree is responsible? Which tree is invalid? So which node is invalid?
Wouldn't it be the topmost?
Sorry?
Wouldn't it be the topmost node?
Let us make the stop mode is correct. Root is correct. Except the root. Seven, you see, right? 7. Did you notice the 7 is greater than 6, right? So 7 should go to the right side of 6. So actually 7 should be here. So this is the problematic one. Does anyone has any question about this?
No, that makes sense.
Okay. Okay, so maximum depth of a BST can be big O n. Why? I just showed a few minutes ago that a BST can grow linearly. So that is the max for the worst case. But in general, average depth is like this. So log and with base log means here base 2. Okay. Now let us quickly go through the insertion operation of a binary search tree. We saw that whenever we illustrate with some data, we saw this. How do we insert a value to a BST? So these are the rules or in the algorithm. These are the steps for the algorithm. Number 1 is the newly added element. Okay, for instance, the QS, we say key in a to a BST always be a leaf node. So it cannot be middle. Okay, so a new node cannot put in the middle, cannot be put in the middle. It cannot replace or override any existing values. Okay, and the process is recursive. Recursively it goes, and then so how do we put the recursive model? So the recursive for all nodes we need to do. Okay, compare x to root. Start from the root. Okay, so if x is equal to root, then do nothing. Okay, so that is the and say that the element already exists in the tree in the BST. In the BST, there are 3 main criteria. One is that all root node is greater than left child, left node, and less than the right node, and there cannot have any duplicate node. So if you have any node on this X, and if that already exists, so then nothing, and say that it already exists. Okay, and say then if X less than the root, so then X needed to be added in the left subtree, and X is greater than root, then X go to right subtree. If root is empty, then X has a leaf node at that place, so wherever the root is empty. Okay, so for instance, in this way, what we do, we say recursively. That means, let me go to some previous slide. So from here to here, so whenever we consider some, in the first step, we need to consider this is as the root. And the second, recursive means, so then we'll go this side and this is root. And then we will go down, this is root. And we'll go down, this is root. Okay, so the recursive means we will start from the top and go down, go down, go down. So time complexity is the depth of the tree. So if it is like a balanced binary tree, then depth will be log n. Otherwise, it may be maximum big O n. Okay. So you know that, for instance, we got 6, right? The 6 will go top, and then we got 2, then 2 will the left side, and then we receive 4, 4 will go right side of 2, and then receive 1, 1 will go left side of 2, and then 8, 8 will go right side of 6, and then 3, 3 will go left side of 4. And then now if we encounter 6, right? Okay, so this is another tree. This is another tree, so it grows like this way. Okay, for the test, day after tomorrow, tree is not covered, right? So after the test, you please practice. Take a data set in any random order and draw a tree. Okay, so this is the homework. Try it yourself. Okay, with this given data set, draw a binary search tree, then apply pre-order traversal, then in-order traversal, and post-order traversal. What is pre-order traversal? Your root or vertex will be first, and then left child, then right child. Okay, the traversal rule is like here for pre-order traversal, we saw that we should say vertex, then left, and then right. And then in order, the vertex will be in between left and right. And then post order, the vertex will be after left and right. This is the order. So here in a BST traversal, there is no way that you say have right V L, right vertex, then left. Then this is invalid. In all cases, always left child precedes the right child. So in a test, you may be given an MCQ type questions. So which one is invalid traversal? Okay. Let us see what is. So now finding a key, that means finding a number in a binary search tree. That is called search operation. Okay. So search operation is like insertion operation. So it is a part of insertion operation. We said that insertion operation, we recursively compare our element with the root element, and then we move through left side or right side of the element, of the vertex element, and we found where we found a position, and then we put that element as a leaf element. Here something similar, almost similar. For instance, we want to see whether the element exists or does not exist in a BST. Then we will search. This is the algorithm. For instance, return a pointer to the node that key has X if it does not exist, or null if there is no such node. This is the algorithm's main output. Okay. Now let us see how to do this. So if our element is at first search, if its root is null, then that means the tree BST is null. So then there is no way to search. We cannot find anything, right? Okay. Now the second one, if our key, that means X, is equal to the root element, then return the root element and it says X is found. And if X is less than the root element, then go to the left subtree and do the recursive search the same way. Otherwise, if X is greater than the root element, then go to the right subtree. Okay, this process is very simple, and in this way, we will go all the way into the BST, and hopefully we will find it, or we won't find it. So in that case, we'll say it does not exist. Okay, but only another operation in a BST. So this is for searching operation, the algorithm or pseudocode for the searching operation. For BST, okay, you see that this is they have drawn, for instance, whether look for searching for 9. So 9 is less than 15, so they are coming to the left subtree, left side. And then again 9 is compared with 6, so it is greater than 6, so go right subtree. And you see that then the put on the left less than sign and greater than sign on top of a node, so that they just give the comparison result. And the 9 is greater than 7, so it will go right side. Then 9 is less than 13, so it is coming left side. And it is found here. In that case, it's found. For instance, if you do for search for 8 or say 11, okay, same, you would follow the same path, but you say 11 is not found. Okay, so 11, it would come same path. It will follow the same path up to 13, and after here, then it will up to comes this side up to 9. So when coming to 9, so it is not 11, does not match, does not found. It is not found. Okay. Now the only Another thing is that finding minimum and maximum element from a BST. So how do we find the maximum element? So in order to find the maximum element, we need to go right, always right to the right side of the BST. And in order to find the minimum element, we need to go left side. You understand this one? So for this BST, if we want to find the maximum element, the node with maximum value, which side we need to go in? Right side, right? So maximum, that means right side. The 20 is the maximum, right side. We want to go to the right side. And for the minimum element, we need to go left side. Always left. 2 is the minimum. Okay. Okay, but now only the element that is difficult part in BST operation is delete operation. Delete operation is a little bit complicated than insertion and search operation. Before I go through the delete operations, let's see how many are there. Okay, 20 people are there. Let me get the attendance, please. Okay, so let us get the attendance. And Jason. Jason is here.
Yes, I'm here. Hello?
Yes. Got it. Matthew. Daniel. Myers.
Here, sir.
Antonio.
Here.
Jasmine. Teton. Elisa.
Here.
Tyler.
Here.
Tyler is here. Ernest. Angel.
Here.
Ernest is here. I'm sorry.
Okay. Jordan.
Here.
Cody. Isaiah. Jimmy.
I'm here.
Savvy.
Here.
Loyal. Lloyd. Dave.
Here.
Karen. Mikhail.
Here.
Jack. James.
Here. Line 18 is also here.
Okay. Brandon.
Here.
Noah. Ellen. Kenya. Jimmy. Lilivia.
Here.
Jesus. Cameron. Sebastian.
Here.
Alec. Justin. Daniel. Andrew.
Here.
Nicholas.
Here.
Jessica. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's someone did not respond. Is anyone left here? Is anyone missing?
Me, I'm here.
Okay. Yes.
Line 33 said he's here.
Line 33.
Yes.
Alice? Alice,
Yes.
are you here?
Yes.
Okay, we are discussing the delete operation from a BST. So delete operation is a little bit complicated, okay, other than the insertion and searching. So actually deleting means here we do not actually delete the node, we just unlinked the delinked the node. Okay, for instance, we use our social media. So for instance, you have a Facebook friend. Okay, so if you want not to keep him or her anymore in your friend list, so what do? You just unlink him, right? You just unfriend him or her. Then what happens? So his or her account is not deleted actually. What happens? His connection with you is just deleted. Okay. Similarly here, so in a linked list, what happens? So in a BST, you are in a linked list, like a linked list, or in this data structure, kind of data structure, what do you do? So for deleting a node, so let us see this algorithm first. Okay, if node is the leaf node, okay, then just delete it and no other action is required. How do we delete this? So delete this. For instance, let us think that we have a tree. Yeah, we have a tree. We have a tree, for instance, 6, 10, 4, 5, 3, 15, and 8, for instance. Yeah. So we want to for instance, we want to delete a node, for instance 8. And how do we delete that, for instance 8? Okay, so this is 8 is a leaf node, right? So we know that all leaf nodes, for instance, we can think that they have also null. So they have null. They have null. Okay, so here then you can put so this null value or default value or whatever you see you value put over here. So then this will be deleted. the value will be gone. Okay. Now, so if the load is in if node, then delete it and no other action is required. Then done. Okay, if the node has one empty subtree. Okay. So for instance, if I want to delete the node 10, not 8, okay? As an okay, so not this situation. For instance, let me draw this. Not true. 12 over here. So the second case is here 12. For instance, if you have one empty subtree, for instance, we want to delete this one. We want to delete 15. In this case, you want to delete 15. Then what do you need to do? So just append connect the empty subtree to the parent node. So here connect this 12 with this parent. Connect this 12 with this parent. Then, okay. Since it's a BST, it can have only two. So one is existing 8 over here, and then you are connecting 12 over here. So that means 15 will be. Let me go. X has one empty subtree, append connect to the empty subtree. Actually, we can skip. We can even skip this case 2. Case 3 will be integrated with in case 2. For instance, if you say if node has non-empty left and right. Okay, so 2 is for only it's one-sided. So in this here 2 is if we say this way, we're gonna keep this way and then go. But for 3, for instance, if we want to delete, for instance, 10 over here, then what will happen? Non-empty subtree and left and with non-empty left and non-empty right. Okay, it says one empty. That means either left side or right side is empty for case 2. They are meaning this one. For this meaning of 15. For 15, case 2 is for 15. Either left or right is empty. So either left or right. For instance, right side is empty. So here in this case, so this is connect 12 with 10. That's gone. Okay, now. Sorry, I need to write 8, 10, 8, 12, 10, 15. Like this, right? So if, for instance, this 12, it has both non-empty left and non-empty right. So in that case, copy the smallest value from the right subtree. Okay. For instance, whatever we say, for instance, here we have 14 over here, and we have 17 over here. Okay, if we have more. So here the smallest function. So we say the right from take the smallest subtree, smallest value from the right subtree. And then in the last week we discussed that. We told that there are 2 ways. Take the right side and take the smallest value. From the smallest value from the right side will be 14. So these 14 move to here, with 14 over here. Okay. So now, and then this 14 has duplicated, right? Then delete this 14. How do you delete this 14? Just put null value here. Null value over here, then it will be deleted. Okay. So this is the way that any node can be deleted from a BST. Okay. For instance, here, if we want to delete 4, okay, it will fall in case 2. Case 2 has 1. This has one right side is empty, right? So that means in order to delete case 4, ignore 4 over here. So that means it will fall. Okay. In order to delete 4, since 4 has one empty subtree, so this side is empty, right? This side is empty. So this is why then which side is not empty. So take this branch. If it is even it is branch, no problem. Take the whole branch and append it with this. Append it with connect this with. So connection is going there showing up to down. So they put the up to down over here, no problem. And then this will be, so since it is BST, that may have maximum 2 connections. So this connection will be disconnected. And then okay. Now if we want to delete 4, 2 over here, 2, okay. So then take the smallest value from the right side. So which is the smallest value from the right side? 3, okay. So then 3, put this 3 at this, replace 3 by this one, okay. And then again we will have 3. It needs to be disconnected 3, right? And then how do we disconnect, delete 3? Again apply the rule 2, case 2. So then 3 will be again, so make direct connection with 4 and 5. So then in that case 3 will be deleted. How this will be deleted? Because 3 will be the left side. 3 was the left side. I can make 4 from the left side. So then 3 will be deleted. Okay, that's all for today. And then good luck for your test. After tomorrow. Does anyone has any question?
No.
Okay. That's all for today. Thank you so much.
Thank you,
Thank
sir.
you.